Hello, I am Yuqiao from Xian University. I am glad to present our paper, Graph-Based Self-Learning for Robust Person Re-Identification on WACV. This work was done when I was a research intern at Tencent U2 Lab. This work, we focus on addressing label noise problem in person re-ID. Label noise is inevitable in human annotation process because of the visual ambiguity in pedestrian checking video. And the noisy label will lead to performance degradation of our re-identification model. We study 3 types of label noise models in our paper, including class conditional label noise, instance-dependent label noise, and tracklet-level label noise. Let's look at some examples of IDN and TRN. IDN are independent images look similar to the misallocated ID. These mislabeled images may belong to different identities, while TRN samples are multiple samples from the same tracklet, which are a series of consecutive images, and belongs to the same identity. Our goal is to run discriminative feature for person ID with noisy human annotations. We propose the graph-based self-learning framework which iteratively optimizes model parameter in network training phase and rectified the labels of the noisy dataset in label correction phase. In the label correction phase, we construct a sparse affinity matrix by calculating the similarities of each sample's k-nearest neighbors as the edge weights in the graph. Image pairs which looks more similar will have stronger connections in the graph. After constructing the KNN graph, we aim to optimize the label space to be consistent to the contextual information in the feature space. It is performed by label message passing on the KNN graph. Each node in the graph will aggregate label information from its kinetic labels according to the edge weights. After neighborhood aggregation by message passing, if the sample's current label is inconsistent with its label in the graph, regard the sample is mislabeled. Then a new label will be assigned to the sample according to the aggregate information from its neighbors in the KNN graph. After the flow iterations between network training and label correction, both the labels of training data and the performance of the model will be converged. Then we can finish the training. In the label correction phase, some labels of the samples in the training set will be changed. There are 3 types of situations. A true correction is that we turn a wrong label into a right. A false correction is that we turn a right label into false. A switched correction is that we turn a wrong label into another wrong label. We can also calculate the precision and recall of label correction using this formula to evaluate whether the label correction is doing the right thing. If there are more true correction than false correction and switched correction, label noise will decrease and the model should become better. We can observe that the precision of label correction is relatively stable in the training iterations, while the recall rate of label correction is increasing during training, which means more and more incorrect labels are rectified. We can also see that about 80% of IDN can be rectified, while only about 20% of TRN can be rectified. We also test our method with the origin labels of existing re-ID benchmarks, which the labels are considered relatively clean. As we can see, we find that our method can discover some real incorrect annotations in the existing benchmarks and improve the performance on test dataset. We compare the re-identification performance of our method with other algorithms, including robust deep learning algorithm for general image classification tasks with label noise and 2 existing robust deep learning methods designed for person re-ID. The results showed that our method performed better than the existing method on 2 popular re-ID benchmarks under different ratio and different types of label noise. Thank you for listening. For more details, please refer to our paper.